Hello, so we will continue the chapter 14 review on liquids and solids. And we will start from question 6, where we left off yesterday or the other day. And we have done CH3OH and BF3. And so we need to do now Cl2O. And Cl2O was part of the chapter 12 review, and we did the Lewis structure. So I'm going to recall the Lewis structure here. So we have a chlorine surrounding the oxygen, and oxygen has 2 single bonds and 2 lone pairs. So if we look at the table for deciding on the molecular geometry, we have 2 single bonds, 2 lone pairs. That's 4 electron groups in total. So you start looking at the bottom of the table where it says 4 electron groups. And we have 2 lone pairs. So that's the real bottom row of the table, where you have 4 electron groups, 2 lone pairs, and the molecular geometry is bent with an angle of less than 109.5. So we can say that this molecule here is bent. It has a bent shape with an angle of 109.5 around the oxygen, because oxygen has 2 single bonds and 2 lone pairs. So 4 electron groups around oxygen, including 2 lone pairs. Next, you want to look at the electronegativity difference between the oxygen and the chlorine. So for this, we will use the electronegativity. Chlorine has an electronegativity of 3.0, oxygen it's 3.5. So you do 3.5 minus 3.0, it's a difference of 0.5. And a difference of 0.5 is considered polar covalent. So it's polar covalent for the bonds, the single bonds. So now you have to decide, is the molecule polar overall? And so if you imagine having those 2 arrows, for the 2 dipoles here, going up like this, and the other one like this. So they go towards oxygen because oxygen is the most electronegative element of the 2. And so they are not exactly opposite each other, right? Because the shape is bent. So the 2 arrows will actually add up together to make a larger dipole. And so I'm going to steal that arrow here. And it's actually going to be overall dipole like the arrow I just brought in. And so it's a polar molecule overall because the 2 dipoles do not cancel because of the fact that the shape is bent. So they will add up into a larger net dipole that goes from between the chlorines up towards the oxygen, because the oxygen is the most electronegative element of the 2. So Cl2O is polar. So let's move on to SiF4, silicon tetrafluoride. So let me bring in the Lewis structure of SiF4. So you see how SiF4 is, having the silicon in the center surrounded by the 4 fluorines. The 4 fluorines have lone pairs, and then the silicon, because it has 4 single bonds, it has its octet like this. So that's the final Lewis structure for SiF4. Now let's determine the shape. So the central atom is the silicon, and it's surrounded by 4 single bonds, which makes 4 electron groups, 0 lone pair. So let's look at the table. 4 electron groups, 0 lone pair. So we want to look at the row where it says 4 electron groups, 0 lone pair, tetrahedral molecular geometry. And so the molecule has the shape of a tetrahedron with bond angles of 109.5. So let's make that shape on paper now. So this is how you would draw the SiF4 using the conventional 3D way that chemists use. So you have two bonds in the plane, and these are the straight lines. So going from silicon up towards the fluorine on top of it, and then to the left. So these three atoms are in the plane. And then the full wedge is the bond coming towards you, so out of the paper from towards you. And then the wedge that is dashed is going away from you, from the plane of the paper, so it goes behind the plane of the paper. So that's how we represent a tetrahedron. So now let's determine if we have polar bonds. So let's look at silicon and fluorine electronegativities. And silicon is 1.8, fluorine is 4.0. So we do 4.0 minus 1.8. That's, hold on. That's 2.2. And a difference of 2.2, according to the table here, it says that it's ionic. However, we know that silicon is a metalloid, fluorine is non-metal. So together they make an ion. They don't make an ionic compound. They make a covalent compound. So we'll say that it's a polar, and it's strongly polar. Fluorine, being the most electronegative element of all, will always make very polar molecules typically. So we have polar bonds with the arrows going from the silicon towards the fluorine. So I drew dipole moments for each of the bond. So it's four arrows of the same length, because it's pulling with the same strength, and it's pulling in all four directions. So of course it should be drawn on the 3D molecule. So when you have four bonds pulling with the same strength, because you have, the bonded atoms are the same, so they will pull with the same strength. And here they pull in four different directions that are symmetrical, because for fluorine to be as far away from each other, or for the electron groups to be as far away from each other from the silicon, they take a shape of a tetrahedron. And that means they are all equidistant. They are all as far away from each other as possible, and with the same distance from each other, because the bond angles are all the same, 109.5. And so it's a symmetrical structure. And if you are pulling in all four directions like that with the same strength, it will cancel. The four dipoles will cancel. So overall, the molecule will be non-polar, even though it has polar bonds. So we know that the bond is polar, and even though it is polar altogether, because we have a tetrahedral shape, the SiF4 molecule is non-polar overall, even though it has polar bonds. That's because the dipole moment cancel due to symmetry. The four identical dipoles pulling in opposite directions from each other. So this is something you have to remember. When you have a tetrahedron with four atoms of the same kind pulling on the central atom, or it could be the reverse. The central atom could be the most well, typically it's the outside atoms that are more electronegative. So it will cancel. So SiF4 is non-polar overall. So that answers question 6. So let's move on to question 7. What type of intermolecular attractive forces is active in the liquid state of each of the following substances? So we have these substances, and that's, we did this one on the first chapter review for 14, and this one as well. here this is ClO2, Cl2O, sorry. So we have fortunately decided already if these were molecules that were polar or non-polar, and we will use those properties to decide on the intermolecular attractive forces that are active in the liquid state of these substances. So first there is neon, but neon is a single atom. You know, it's the noble gas neon, and it's in group 8A. And we know it's, you know, roaming around by itself, single atoms. So what are the intermolecular attractive forces between atoms of neon in the gas phase? Well, sorry, it says here in the liquid state, because in the gas phase, we know that intermolecular attractive forces are not active, right? And that's why atoms are free from each other in the gas phase. So we need to be in the liquid phase to talk about intermolecular attractive forces being in action. And so when neon is in the liquid state, because it's you know, neutral atom, there is no, you know, dipoles. It's not an ion, so there is no charge. So the only force that can act on neon is the London dispersion forces. Remember that London dispersion forces are the force that is due to instantaneous dipoles, which happens because all atoms have an electron cloud. And so from one moment to another, the electron cloud can be distorted, and you can have a momentary positive charges on one hand and negative charges on the other hand of the electron cloud. And so this creates what we call instantaneous dipoles, and then that creates an attractions between neighboring neon atoms. And we call these attractions the London dispersion forces. So London dispersion forces only because it's a non-polar atom. So now, methanol, CH3OH, what are the attractive forces that are playing in the liquid state of methanol? So for this, to decide what are the forces acting on a molecule, you need to decide if it's polar or not. So let's look back to what we decided for methanol. We said methanol here is polar overall, right? Methanol is polar because it has two polar bonds, the CO bond and the HO bond, that are polar, and that's a bent shape around the oxygen there. And so the dipoles do not cancel, they add up into an overall dipole that is shown here with the red arrow. So this is a polar molecule overall. So then we can say that, so first of all, London dispersion forces, like all molecules, have that. Then it has dipole-dipole interactions because we have a dipole moment. So dipole-dipole interactions are happening because methanol is polar, right? Because we have a dipole. And the last thing you need to decide is, do we have hydrogen bonding or not? For hydrogen bonding to occur, you need to have an hydrogen bonded to an oxygen, a fluorine, or a nitrogen. And here we do have an hydrogen bonded to an oxygen, right? If we look at the molecule again, we do have the hydrogen bonded to an oxygen. So this hydrogen will be attracted to the oxygen of other methanol molecules. And the oxygen of this methanol molecule will be attracted to the hydrogen of another methanol molecule, but not any hydrogen, the hydrogen that is bonded to the oxygen. So yes, hydrogen bonding is possible for methanol, hydrogen bonding, because we have H bonded to O. So methanol molecules will be attracted to each other, from the hydrogen and the oxygen that are bonded together. So that's for methanol. Now, BF3, boron trifluoride. So as always, there is London dispersion forces. All molecules experience London dispersion forces because they all possess an electron cloud, right? They are made of atoms. Atoms have electron clouds, so every electron cloud can be distorted and experience London dispersion forces. Now we need to see if BF3 is polar or not. So let's go back to what we decided for BF3. We said BF3 here. So it has polar bonds. It's trigonal planar though. So it's non-polar overall because the 3 polar bonds are identical and pulling in opposite directions symmetrically around the B. And so their dipole are cancelling. So this is not polar overall, even though it has polar bond, a little bit like SiF4. We have polar bonds, but this is a symmetrical structure, and we have boron surrounded by 3 fluorine, so they all pull with the same strength, and they are pulling in symmetrical ways, because that's the way for them to be, as far away from each other as possible. So overall, this flat molecule here is non-polar. So if it's non-polar, it cannot experience dipole-dipole interactions, right? So there is no dipole-dipole interactions. Now the question, does it have hydrogen bonding? Well, if you look at the formula, there is no F there. So there is no hydrogen bonding possible. So that's it. It's only experiencing London dispersion forces only because BF3 is non-polar and there is no H in the formula, no H in this molecule. No H, and the H is, as long as there is no hydrogen, then you cannot have hydrogen bonding. So that settles it for BF3. And now Cl2O. We just did it above here. Cl2O, we decided as a bent shape, and it's polar overall, right? Cl2O is polar overall because the two dipoles do not cancel. They do not cancel because the molecule is bent. So we do have a dipole here. So we can write already that we have London dispersion forces and dipole-dipole interactions because Cl2O is polar. So next we need to decide, do we have hydrogen bonding? And here again, we have no hydrogen. So then it cannot experience hydrogen bonding. So dipole-dipole interactions because it is polar, but no hydrogen bonding because there is no H also in this molecule. So that's how you decide what are the intermolecular attractive forces that are acting on molecules of the same substance. So next question, classify the following substances in order of increasing boiling point. We have ethane, CH3CH3, ethanol, CH3CH2OH, and propanol, CH3CH2CH2OH. So ethanol and propanol are alcohol. We see that from the OH function here, functional group. And so to justify your answer, you will need to list the intermolecular attractive forces that are acting within each substance. And to decide on the intermolecular attractive forces, we need to decide if we have polar molecules or not. And to decide if we have polar molecules or not, we need the Lewis structure. So the first step is to get the Lewis structures of each. So let's get ethane. So ethane, CH3, CH3. So we have the 2 carbons in the center. surrounded by the 6 hydrogens. So we only have single bonds. So next you need to decide, do we have polar bonds? So we know the CC bond will be non-polar because it's 2 atoms of the same kind. Now let's look at the CH. Carbon has an electronegativity of 2.5, hydrogen is 2.1, so that's a difference of 0.4. 0.4 is considered non-polar, so we do not have any polar bonds. So can ethane be polar? No, if you have no polar bonds, ethane cannot be polar. So ethane is a non-polar molecule. So as a non-polar molecule, what are the intermolecular attractive forces that it experiences? Well, it will be only London dispersion forces, because as a non-polar molecule, it cannot experience dipole-dipole interactions. And the hydrogens here are not bonded to oxygen, fluorine, or oxygen, fluorine, or nitrogen. So they cannot have hydrogen bondings either, right? So this molecule only experiences London dispersion forces. Let's draw the Lewis structure of ethanol now. So ethanol is the same as ethane, except that you will change one of the OH, as one of the hydrogen as a OH. That's the only difference. So then the Lewis structure looks like this. Very similar, except that you have a OH this time. And so here the oxygen, if you look at the oxygen, it's surrounded by 2 single bonds and 2 lone pairs. 2 single bonds, 2 lone pairs. Let's look at the molecular geometry shape. When we have When we have 4 electron groups, because 2 single bonds, 2 lone pairs, that's 4 electron groups, and then 2 lone pairs. So you look at the bottom row of the table, and the molecular geometry is bent around that oxygen with a bond angle of less than 109.5. So the way it's drawn here is quite helpful because it shows how it is bent around the oxygen. Because of those 2 lone pairs, we have a bent shape. And so let's look at the polarity of the bonds first. So do we have polar bonds? We have CO and CH. We know already the CH and CC bonds are non-polar, but now we have CO and OH bonds. Between carbon and oxygen, 3.5 minus 2.5, there is a difference of 1.0, so that's going to be polar. And between oxygen and nitrogen, 3.5 minus 2.1, that's a difference of 1.4, and that's also polar. So those 2 bonds are polar. So the CO bond and the HO bond are polar, and they're polar towards oxygen. The 2 dipoles would be pointing towards oxygen. And because it is bent, they do not cancel. So the polarities do not cancel. And so the molecule is polar overall. So we have placed the net dipole. So the net dipole represents the overall polarity for the molecule. So because the 2 dipoles for the CO and HO bond are adding up, they are, making a net dipole that goes between the C and the H and going up towards the oxygen. And so the molecule is polar overall. So we know it will experience London dispersion forces, dipole-dipole interactions, because now we know it's polar. And the question is, does it experience hydrogen bonding? And here we have hydrogen bonded to oxygen. So yes, we can have hydrogen bonding because we have hydrogen bonded to oxygen. And that's one of the atoms that is a condition for hydrogen bonding. So that means ethanol will experience London dispersion forces, dipole-dipole interactions, and hydrogen bonding because one H is bonded to oxygen. And that's thanks to this OH bond. So now let's look at propanol, CH3, CH2, CH2OH. So propanol will be very similar to ethanol, except that there is one more CH2 in between the CH3 and the CH2. So it looks like this, the Lewis structure. So here is the Lewis structure of the propanol. So very similar to ethanol, except that there is one more CH2 in between the CH3 and CH2OH. So we have the same configuration here around oxygen. So oxygen will have a bent shape because of the two lone pairs. And the CO and OH bond are polar. And so we can say that this molecule is also polar, the same way that ethanol was polar. So it's polar towards oxygen because the two dipoles from the CO and HO bond are adding up into this net dipole that I have drawn now. So we have a polar bond, which means that about the intermolecular attractive forces that propanol is experiencing, we can list London dispersion forces, dipole-dipole interactions, and hydrogen bonding, because again, we have this H bonded to the oxygen. So propanol experiences very similar intermolecular attractive forces as ethanol, right? The London dispersion forces, dipole-dipole interactions, and the hydrogen bonding because of the H bonded to oxygen. But there is a difference between these two, right? It's the size of the molecule. And that's important when you are comparing molecules that are, the same otherwise, right? They experience the same forces. And so the only difference is in the size of the molecule. And that will play out in the London dispersion forces. The London dispersion forces depend on the size of the molecule because it's all about the electron cloud. And the electron cloud around ethanol is smaller than the electron cloud around propanol, because propanol is a larger molecule. There is more atoms there. So there is a larger electron cloud. And so when you distort a larger electron cloud, you create stronger instantaneous dipoles. So the London dispersion forces are stronger, slightly stronger in a larger molecule versus a smaller molecule. So the London dispersion forces will be slightly stronger in propanol than ethanol. So this will mean that the boiling point, because all of this is to decide about the boiling point. So the boiling point of propanol versus ethanol will be higher because you have stronger London dispersion forces, right? Because molecules that experience the strongest intermolecular attractive forces will have the higher boiling point, because you need more energy to break those intermolecular attractive forces to, go from the liquid phase to the gas phase. And so stronger intermolecular attractive forces will mean higher boiling point. So propanol will have a higher boiling point than ethanol. And then ethane is really different here because it only experiences London dispersion forces. So it's weakly held together, right? It's not very strong forces holding the molecules together. So that means it's going to be easy to bring to the gas phase. You will need less energy to boil the liquid into a gas. So ethane will have the smaller boiling point of all three. So it comes down to this. The smaller boiling point will be for ethane because it has the weakest intermolecular attractive forces, having only the London dispersion forces. then ethanol, and then propanol. And ethanol is expected to have a lower boiling point than propanol because its London dispersion forces are less strong than in propanol. So here, the full sentence. So now we can move on to question 9. You seal a container partially filled with colored water. So there is a picture here to illustrate that. Which best describes what occurs in the container? So you have A, B, C, D, E options there. So A, water evaporates until the air becomes saturated with water vapor, and at this point no more water evaporates. B, water evaporates until the air becomes overly saturated, so supersaturated with water, and most of this water recondenses, and this cycle continues until a certain amount of water vapor is present, and then the cycle ceases. C, the water does not evaporate because the container is sealed. D, water evaporates, and then water evaporates and recondenses simultaneously and continuously. And E, the water evaporates until it is eventually all in vapor form. So the correct answer is D. The water evaporates and here. The water evaporates and then evaporates and recondenses simultaneously and continuously. The other options are not correct. So let's say why. Water evaporates until the air becomes saturated with water, and at that point, no more water evaporates. That's what's not true is that no more water evaporates. It's not true. The water will always evaporate and then recondense. As soon as there is vapor, then it recondenses, and you have what we call an equilibrium. So what was wrong here is no more water evaporates after a while. In B, the water evaporates until the air becomes overly saturated. It's not necessarily true here that it becomes overly saturated. Then most water recondenses, yes, and the cycle continues until a certain amount of water is present, water vapor is present, that's true. But what is not true is then the cycle ceases. That's not true. The cycle does not cease. It keeps, evaporating and recondensing all the time. The water does not evaporate because the container is sealed is not true. You know that it can evaporate even if it's sealed. And it evaporates until it is eventually all in vapor form. No, if it's at room temperature, there's no reason that it would be all in vapor form. So that's what you needed to choose, D. And so I have an illustration here to really help you understand this. So water evaporates, and let me show the whole thing here. So water evaporates. If you look at the schematic here, A, once you have put some water and put the cap on, you will have a net evaporation occurring at first. So because at first there is no water vapor, so only evaporation occurs. So that's why the sentence was saying, water evaporates. So the amount of liquid decreases slightly. Yeah, usually it's barely, it can be visible, but it's usually barely visible. And then as the number of vapor molecule increases, the rate of condensation increases. So now that we have vapor above the liquid, we can have condensation because condensation can only happen once you have vapor formed. And so this will increase the rate of condensation until the rates of condensation and evaporation are the same. They will be equal, which means you have as many evaporation as you have condensation, which means you have the same amount of water vapor above the liquid and you keep the same amount of liquid. So we have reached what we call an equilibrium. where the amount of vapor stays the same, the amount of liquid stays the same, but it's a dynamic equilibrium because it's still happening. Evaporation and condensation are still happening at the same time and at the same rate. That's why, it's an equilibrium. But it's a dynamic equilibrium here. It is important to understand that it's still happening. Evaporation and condensation are still happening. So that explains this question. So final question, what do we mean when we say a liquid is volatile? Do volatile liquids have large or small vapor pressures? What types of intermolecular forces occur in highly volatile liquids? So what does it mean that a liquid is volatile? So volatile means you have a lot of vapor above the liquid. It is volatile when there is a lot of vapor above the liquid. Sorry. Or when you have a large vapor pressure above the liquid, then you have a lot of vapor. So that means you have a lot of vapor pressure above the liquid. And a volatile liquid will be volatile because it experiences weak intermolecular attractive forces. You need a liquid that has weak intermolecular attractive forces, so you will have enough molecules that have enough energy to go into the gas phase, from the liquid phase into the gas phase, and that's why you will have all this vapor above the liquid, because the molecules are not held very strongly in the liquid, so they can escape into the vapor phase easily. For example, liquids that experience only London dispersion forces will tend to be volatile. And we know that liquids that experience only London dispersion forces are, liquids that are non-polar. So yes, non-polar liquids will tend to have a lot of vapor pressure above them and be volatile.